This is the alternating current tutorial presented by the SHLTV. Hello, welcome to a new tutorial presented by the SHLTV. In this tutorial, we're going to see alternating current. In the introduction, we need to know that alternating current is the main current via which current electricity is transferred to households. Current electricity is not transferred via direct current but via alternating current because of several factors. The first factor is that the power dissipated inside the current cables is going to be equal to I squared R, and this power dissipated, this I inside with direct current is going to be the I in the circuit. In case of alternating current, the I is supposed to be the I effective, and the I effective is given as I0 all over the square root of 2. So realize that the I effective in the AC is mostly going to be less than the I in direct current. So this is the first reason why AC is much more important in the transmission of current via long distances compared to DC. The second reason is that the AC current can be stepped up and stepped down when you are via transformers using the Faraday's law of electromagnetism, as you have seen in electromagnetism chapter. So now, alternating current and voltage. What is alternating current and voltage? This refers to current and voltage which changes both its magnitude and direction as time progresses. It's very important for you to note the point, magnitude, and direction because all of them are going to be used in the latter sections. So now, here are going to be the different waveform or different type of alternating current. Alternating current with square waveform is represented as such here. You see that here is a constant magnitude, then descent changes its only direction, but the magnitude is going to be similar. The second part is going to be a sawtooth waveform. The sawtooth waveform, so this is I equals 0 and I equals to -0. With the sawtooth waveform, you have this. It increases magnitude, then changes direction, increases again to magnitude, then changes direction. And lastly, we are going to have a sinusoidal waveform. With the sinusoidal waveform, you only have this. Now, we are going to study this sinusoidal waveform inside this chapter more specifically. Now, in this sinusoidal waveform, you see that I is equal to I0 sine omega t, where omega t is theta, and V is equal to V0 sine omega t, where omega t is still theta. Now, mostly for all the current inside the circuit, say that I is equal to I0 sine omega t plus phi, where phi is going to be the phase difference, and here phi is also going to be the phase difference. So now let's speak about what is the effective current and the effective voltage. We need to know that the average current of this circuit. So if you find the average here is going to be the integral of all the currents inside the circuit. If you sum all the currents here, so from summation from I is equal to 0 to n of I of ik, from the summation of k is equal to 0 to n of ik is equals to the integral. We're going to integrate it from 0 to the period of all these different values here and divide it by the total period. So when we are going to integrate this function here, you're going to realize that the average current is always going to be 0. So the integral, when you sum and find the average current in this particular graph, you'll realize that the average current is going to be 0. But at homes, when I'm in my house now, I have lighting inside my home, and this lighting comes from an AC circuit. Now the question is, the current can never be 0 because when you plug a bulb on an AC circuit, you realize that bulb shines. So it implies that there exists an effective current which flows in an AC circuit, and that effective current must be found. So in order for you to find out effective current, you must start from the formula P is equals to I squared R, and we are going to say that I is going to be the effective current. So the power average is going to be equal to I1 squared R plus I2 squared R plus all this. So the power average is going to be equal to R all into I1 all this. So the power average is equal to R, the summation of K equals to 1 to N of I squared K all over N, the total number of currents inside the circuit. Now we need to know that this is the summation. The summation is used in case of discrete circuit, in case of discrete variables. But now we are involved with this sinusoidal waveform, and a sinusoidal waveform is a continuous variable spectrum and not a discrete variable spectrum. With continuous variable, summation is said to be integral. So we are going to have power average equals to R. We integrate it from 0 to t of I squared all over the N here will become the period. So, and this is going to start from 0 and N to N, which is the period. So divided by t. So when we are going to say power average is going to be equal to R all over t integral from 0 to t to I squared dt. So now the I is equal to I0 sine omega t. When we integrate this, we put the square here, we are going to have this. But you know that sine squared theta is equal to 1 minus cos 2 theta all over 2. So when we substitute it here, you're going to have this. So I0 move out, so we have R I0 squared all over t integral of 0 t half dt minus integral from 0 to t cos 2 omega t. So when you integrate it, you are going to have the period all over 2. When you integrate it is 1 all over differentiation of the interior, 1 all over 2 omega negative sine of omega t. So it does not change sign here. So you are going to have this at the end. So now placing the limit, when you are supposed to place the limit from 0 to t, we say that here when you place the limit from 0 to t, we are going to say that 0 sine 0 is going to be 0, and you are going to have this. But omega is equal to 2 pi all over the period. So when you substitute omega 2 pi over the period, you have t all over 2 minus t all over 2 pi here. So t 2 pi t all over t here. So sine 2 pi is going to give you 0. So this is why you're going to have all this power average equals to R I0 squared all over t into t all over 2. So this and this is going to cancel. So the power average is going to be R I0 squared all over 2. So this is the power average. But we know that the power average is also equals to I squared effective times R. So I squared effective times R is equals to R I0 squared all over 2. So R times R and R are going to cancel out. So we say that I effective is equals to I squared 0, the square root of I squared 0 all over 2. So I effective is equals to I0 all over the square root of 2. So this is the formula for the effective current which passes through the circuit. Effective current which passes through the circuit is equals to the maximal current divided by the square root of 2. The effective voltage 2 is equals to the maximal voltage divided by the square root of 2, and the power is going to be the effective current and effective voltage. So it's giving us this. So now let's visualize resistance, reactance, and impedance. Now in this circuit, when you visualize this circuit here on the left side and this circuit on the right side, there are certain similarities that you have to put in mind. The point number one, before we see the similarities, is that capacitors and inductors do not act as capacitors and inductors when they are placed in AC circuits. Capacitors and inductors do not act as capacitors, as normal capacitors and inductors when they are placed in AC circuit. In DC, capacitor act to store charges with electrical energy, while inductors act to oppose the rate of change of current. But in AC, both capacitors and inductor act to resist the current flow, and the resistance they are going to have are not going to be called resistances, but they are going to be called the reactance of the capacitor and the reactance of the inductor. So both the capacitor and the inductor resist the current flow and inside the AC circuit. So you see that all these are going to be actually resistors inside AC circuit, and this is a comparable DC. So let's compare this DC. In this DC, you see that you are going to have R1, R2, and R3. In this AC, you are going to have R, XC, and XL. All these are going to be resistors, and all these are going to be resistors. Now we need to know that this XC corresponds to this R2 here, and this XL corresponds to this R3 here. Now there in this circuit on the right hand side, you can find the total resistance here, and this total resistance is going to be R1 plus R2 plus R3. But in this circuit on this left hand side, the total resistance is not called the total resistance, but it's instead called the impedance of the circuit, and this impedance of circuit is given as Z. We are going to find Z as we are going to visualize the latter sections. So now let's visualize the resistors. Now in the above section here, we have visualized the magnitude of the current. We said that alternating current is one which changes both in magnitude and direction with respect to time, and alternating voltage is one which changes both in magnitude and direction with respect to time. Now we have already visualized here the magnitude of the current and the voltage which are going to be used inside circuits. But now in these latter sections with resistors, inductors, and capacitors, we are going to visualize now the direction of current and voltage used in circuits. So now let's visualize the direction of current and voltage used in case of resistors. In case of resistors, you know that by Ohm's law, voltage is going to be IR. So you see that I normally is equal to I0 sine omega t. So our voltage is going to be equal to I0 I sine omega t. So I0R is given as V0. So V is going to be equal to V0 sine omega t. So this is the value for voltage, and this is the value of current. So now we are going to use now a Phasor diagram in order to represent the direction of current and the direction of voltage. Point number one, on the Phasor diagram, the current is always going to be the reference direction, because current is always equal in series, while the voltage is going to be different both in its magnitude and direction in series, while current is equal in both in its magnitude and direction in series. So now we see that the current for the resistor is going to be on the RE here, because the angle they are going to form with respect to the horizontal is going to be 0. So that phase difference is going to be 0. So we have the current here, we have the resistance occurring here, and we have the voltage occurring here. So all of them are going to be lying on the RE. So this is a Phasor diagram. And what is a Phasor diagram? A Phasor diagram is an Argand diagram, or a complex number diagram, which shows the direction of current and the direction of voltage, the direction of current, the direction of the resistances, and the direction of voltage in this Argand diagram, or the complex number diagram. Now we initially said that we have found for the magnitude of current and the magnitude of voltage are being the V effective equals to V0 over the square root of 2. But now we are supposed to find the direction of current, the direction of the voltages. For the resistor, the direction of the current and the voltage are in the same direction. All of them lie on the real number of Z. So now let's visualize now for inductors. We know that the formula for inductor is VL is equals to LDI all over dt. Now I, we know that is going to be equal to I0 sine omega t. So this is a value of I is equal to I0 sine omega t. So when we substitute here and we differentiate, we're going to say that VL is equal to L omega I0 cos omega t. So this is a value here. So from this function here, from this equation here, we can sort out two main things. We need to know that L omega I0 first is equal to V0. So V0 is given as I0 XL. And this I0 XL is also going to be equal to L omega I0. It implies that the reactance of the inductor is going to be equal to the inductance times the angular velocity of the alternating current times omega. Now we see that in this case, we see that the direction of current is written with sine omega t, while the voltage is written with cos omega t. So the direction of the current and the direction of the voltage are going to be different, because we know that cos theta in mathematics is equal to sine of theta plus 90 degrees. Since cos theta is sine of theta plus 90 degrees, so we can substitute here in this equation. We're going to have VL is equal to I0 XL sine of omega t plus 90 degrees. Since it's sine of omega t plus 90 degrees, so in order for, so we realize that what this V, the voltage of the inductor, is going to be in front of the current of the inductor by 90 degrees. So here you have a plus 90 degree here, while here there is no 90 degree. So it implies that the voltage on the inductor is going to be in front of the voltage or in front of the current on the inductor by 90 degree. This is why the representation of the voltage and current is shown as such. So here is going to be the current direction, and here is going to be the voltage direction. So voltage of the inductor is going to be 90 degree to the current. So it's going to lie on the imaginary line of Z. And you should note that voltage and the resistances or the reactance are always in the same direction. So now let's visualize capacitor in AC. So let's see, so in this case here is inside the capacitor. So if you have a capacitor, VC is equal to Q all over C. So now you are going to have here, so since VC is equal to Q all over C, we see that dV all over dt is equal to 1 all over C dQ all over dt. So here you are going to say that I is equal to C dV C all over dt. So let's say V is equal to V0 sine omega t. So when we substitute here, we are going to solve IC to be equal to omega C V0 cos omega t. So there are two main things you can find from this equation. We first have here, we need to know that XC is equal to 1 over omega. This is because I0 is equal to V0 all over XC. And when this is equal to I0, so C omega V0 is equal to V0 all over XC, which is equal to I0. So now this and this can cancel. It implies that XC is equal to V0 all over omega C. So XC is equal to 1 all over omega C, where omega is angular velocity, which is equal to 2 pi frequency of the alternating current times C, and C is always measured, usually measured in microfarad, but in this case, in order to solve, you have to convert it into farad. Now we need to know that again the current was written as IC C omega V0 cos omega t, but now we know that cos theta is equal to sine theta plus 90. So when you substitute, you're going to have IC is equal to C omega V0 sine omega t plus 90 degrees. So we see that the current is always going to be, in this case, the current is going to be in front of the voltage, because here the voltage was taken as V0 sine omega t. So in this case, the current is going to be in front of the voltage by 90 degrees. But we initially said that in this circuit is going to be in series. So it implies that since it's in series, the current is always going to be same the similar in both in magnitude and direction. So the current is all going to be lying on the RA, but the voltage is going to be the difference. So we see that here, since the current is in front of the voltage by 90 degrees, so the current is going to be lying here, and the voltage is going to be lying in this direction. This is the voltage of the capacitor. So now AC circuit with combined circuit elements. So now in case now when you combine now the resistor and the capacitor together, so we combine resistor and capacitor in AC circuit. So when you combine the resistor and capacitor together, we are going to have now this particular Phasor diagram which is going to be produced. So we have the XC which is in this direction, the VC which is in this direction, we have R in this direction, we have current in this direction, we have VC in this direction. The resultant produced will be in this direction here with an angle theta here. So we see that the current, the complex number of the current is going to be equals to I plus I. This small I is the complex number notation. This is the imaginary part of the complex number I0. So since there is no imaginary part of the current, so it's going to be I plus I0. So the magnitude is going to be given as I, and this magnitude is going to be equal to the effective current, and this effective current is I0 over the square root of 2. And the direction is going to be theta equals to tan inverse of the 0, which is the y part, all over the I. So theta is going to be equal to 0 degree. Now the voltage of this circuit here, which is going to be combined in series, is going to be this voltage, which is going to be VR plus I, the negative component, the negative IVC. So the voltage is going to be given, the complex number notation of the voltage is going to be given as such, VR minus IVC. So from this complex number notation, you can find out the magnitude of voltage as being VR squared plus VC squared, and the direction to be equal to tan inverse of VC over VR. But now you need to know that it is lying in the fourth quadrant. Since it's lying in the fourth quadrant, the direction can be written as negative theta, or being written as 360 minus theta. Now the impedance, the complex number notation of the impedance will be written as R minus IXC. So you have here R in this direction, you have I which is in the negative imaginary line. So you have R minus IXC. The magnitude of this impedance will be equal to square root of R squared plus XC squared, and the direction is given as theta equals to tan inverse of XC all over R. But this direction lie in the fourth quadrant, so it implies that direction is equal to 360 degrees minus theta, or direction is equal to negative theta. Now you have the resistor inductor AC circuit. The resistor inductor AC circuit, now in this circuit here, you realize that you are going to have a summation of both the resistor and inductor when they have been placed together. So the current will be always referenced in this direction, resistance will be in this direction, and voltage will be in this direction. But the voltage of the inductor will be in this direction, the reactance of inductor will be in this direction. Now the resultant direction will be as such here. So you have current being written as I plus I0, with the magnitude being I, and that magnitude is the effective current, and the direction being 0. The voltage is going to be VR plus IVL. The magnitude of that voltage is going to be square root of V squared R plus VL squared, and the direction will be equal to, will be lying in the first quadrant. That's theta is equal to tan inverse of VL all over VR. The impedance now is going to be R plus IXL, and the magnitude of that impedance is going to be square root of R squared plus XL squared, and the direction is going to be equal to tan inverse of XL all over R. Now let's say you have capacitor inductors AC circuit. Now with capacitor inductors AC circuit, in this case you are going to have this other one. You need to know that you are not involved with resistors here, so you are not going to have the resistors and the VR line in this direction. We are just going to have the capacitor XC is here, the reactance of capacitor X is going to be here, and the voltage of capacitor is going to be here. We're going to have the reactance of inductor being here and the voltage of inductor being here. All the summation are going to vary with respect to the magnitude of the inductor and the magnitude of the capacitor. So the resultant impedance and voltage produced depend on the magnitude of the reactance of both the capacitor and inductor and the voltage drop on both. So now when you have this, we now see that the current written is always equals to I plus I0, and the magnitude is going to be equals to I, which is the effective current. The angle is going to be 0 degrees. Now the voltage will be equals to 0 plus I, because since all this lie in the imaginary direction, so there is no component of voltage in the real axis, so it's going to be 0 plus I into VL minus VC. So the magnitude the magnitude of this will be the square root of 0 squared plus VL minus VC all squared. So when you have this, you are going to see the magnitude of voltage is going to be VL minus VC. Now the direction of the voltage is given as theta is equal to tan inverse of VL minus VC divided by 0 degree, which is x. Now this is equal to infinity, so direction is going to be 90 degrees. So theta is going to be 90 degrees. So do you know that this is going to exist, infinity is going to exist when you are at 90. So this is why you have seen that you have used 90 degrees. So 90 degrees is the angle that is going to separate both is the angle that is going to separate so 90 degrees is the angle that is going to separate the inductor from the capacitor. So that's the angle that is going to separate both of them. So when you're going to substitute, you're going to have 90 degrees here. We have again impedance. So we either have 90 degrees here. We have again impedance here, Z. The impedance, the complex number notation of the impedance is going to be given as 0 plus I into XL minus XC. So the magnitude is going to be given as this, and the angle is also going to be 90 degree. Now let's say you have resistor, inductor and capacitor AC circuit. The resistor, inductor, capacitor AC circuit, you are going to have now the I current is always going to be similar, and that's going to be I. This I is also going to be I effective, and the angle is also going to be 0. So the voltage in this case is going to be the voltage of resistor plus I, imaginary component of VL minus VC. So the magnitude of that voltage also is going to be equal to the square root of VR squared plus VL minus VC all squared. And the angle is going to be tan inverse of VL minus VC all over VR, or and it close. Now you need to know that this is going to lie either in the first quadrant or in the fourth quadrant, depending on the value of VL and VC. Now if VL is greater than VC, then the voltage is going to lie on the first quadrant if VL is greater than VC. Now if is going to rely on the first quadrant, and if it lies in the second quadrant, the direction is going to be equal to theta. Now in case where VC is greater than VL, then it's going to lie on in the fourth quadrant, and the direction is going to be equal to 360 degrees minus theta, or direction is going to be equal to negative theta. Now the impedance is going to be equals to R plus I into XL minus XC. XL is the reactance of the inductors, and XC is the reactance of the capacitor. So now the magnitude is going to be the square root of R squared plus XL minus XC all squared, and the angle theta is going to be equals to tan inverse of XL minus XC all divided by R. So now let's visualize what is resonance. Resonance refers to the state at which atoms of material vibrate with maximal frequency. So now resonance can be used in either the emission of frequency or the reception of frequency. Now we need to know that resonance is applied at the level of our radio which are at home. So we need to first point that there exists first a bandwidth that our radio signals, that our radio are going to receive certain signals. Let's say RFE is an example. RFE usually have a bandwidth from FM 103.5 to FM 106.5. That bandwidth is going to be 106.5 minus 103.5. So this bandwidth is the are the set of frequency with which you can hear a certain radio station. So the set of frequency that can hear a certain radio station is going to be referred to as the bandwidth, and the bandwidth of the RFE is from FM 103.5 to FM 106.5, and this difference is going to give you the bandwidth. So now we need to know that the bandwidth is equal to the resonance frequency all over the quality factor Q. So now bandwidth is also defined as the maximal frequency, in this case going to be in the FM 106.5 minus minimal frequency, in this case going to be FM 103.5, and all this is going to be equal to F0 all over Q. So now let's try to find what is the resonance frequency. The resonance inside an AC circuit is going to exist when the reactance of the inductor is going to be equal to the reactance of the capacitor. The reactance of the inductor is going to be equal to omega L, while the reactance of the capacitor is equal to 1 over omega C. So omega L is going to be equal to 1 over omega C. When you have this, you have omega squared is equal to 1 over LC. So you know that omega is equal to 2 pi f. So when we are going to substitute, we see that f squared is equal to 1 all over 2 pi all into squared LC. So here we see that f0 is equal to 1 all over 2 pi the square root of LC. So now let's visualize what is the quality factor. The quality factor is the amount of energy stored in a circuit compared to one dissipated. So the amount of energy stored in a circuit with respect to the one dissipated is called the quality factor. So energy stored all over energy dissipated is said to be the quality factor. Energy stored is due to the capacitor, so it's going to be the power stored times time divided by power dissipated times time. So this and this are going to cancel. So we are going to say that Q is equal to I squared times XC. XC is what? XC is the reactance of capacitor divided by I squared R. So when you have this, I and I are going to cancel. So we are going to say quality factor is going to be equal to XC all over R. But you know that XC is equal to 1 all over omega C. So Q is equal to 1 all over omega RC. But we initially found here that omega is equal to 1 all over the square root of LC. So from this formula above, where omega squared is equal to 1 over LC, omega is equal to 1 over square root of LC. So when substituting in this formula here, you can have Q is equal to the square root of LC all over RC. So but C is equal to the square root of C all squared. So we are going to have R into square root of C here, with the numerator being the square root of LC. When you substitute all this, you are going to have the square root of L all over R the square root of C. And the formula for quality factor is going to be equal to 1 all over R the square root of L all over C. So this is the formula for quality factor. Now, since you have found for the formula of the F0, the resonance frequency as being 1 all over the 2 pi the square root of LC, and you have found the formula of quality factor to be equal to 1 all over R the square root of LC, we can now use these two formulas here to find now here the bandwidth. If I substitute 1 all over 2 pi the square root of LC and I place divided by 1 all over R the square root of LC, I'm going to find now the bandwidth, and that bandwidth is going to be the frequency maximal minus frequency minimal at which you are going to hear a certain radio signal. So from here we have visualized all the different sections involved with AC circuit, and the application of this AC circuit is that you can have a radio you have radios which can receive certain signals from radio stations, and these radios have a certain bandwidth where you can hear the radio signal. The bandwidth show the different regions at which the uppermost and the lowermost region at which you can hear that particular radio signal, but the resonance frequency is the internal or the middle frequency at which you are going to hear the radio signal with the best quality. So this is going to be f0, and that bandwidth is going to be equal to f, the f boundaries, which are f max minus f minimal, and it's also going to be equal to the resonance frequency divided by the quality factor. So we have visualized our AC circuits and or what is involved inside. So say thanks for your kind attention. Please don't forget to like and subscribe for Sense Makers. Thank you.